So now let's consider another situation of y going to positive infinity. So the geometry is like that. And now the main difference is that when we take our contour, which goes and comes from plus infinity and goes back, and decompose it in stationary paths, then of course this cancellation, which you have seen on the previous case of y negative, doesn't happen. And in fact, there are two contributions which come across the saddle point. One is above the cut and another is below the cut. Actually, this situation is quite similar to the case considered by you in the model devoted to the quantization of the energy levels in the potential well. But let us now recapitulate how the calculation goes. Here you need to consider contribution of both sides of the cut, and the asymptote becomes 1 over 2 pi I, and integral dz over z to n plus 1. And here you have the same factor, which is equal at both sides of the cut. And now something less trivial. There are two contributions in the square bracket, and one comes from the from above the cut, which is minus 1, and another comes from below the cut. And this term appears because of change of the phase of the variable z. Note that I didn't include plus 1 here because it is trivially cancels. Afterwards, the integral can be calculated, and it happens that the result becomes proportional to. Recall that our n, which stays in the exponent, is much smaller than 1, which basically means that this expression can be expanded, and this expansion gives, after cancellation of 2 pi I, gives simply minus n. So this goes after joining these two factors, and there is also an integral which is dominated by the saddle point. So explicitly, and most importantly, of course, as usual, this integral can be estimated by here we're just dealing with a simple Laplace type calculation, and this integral can be estimated with some prefactor, evaluation of which is your homework problem. But the most important contribution is this exponent at the extremal point, and this is nothing but 2y squared minus y squared. That is just y squared. So as a result, this f of y is proportional with some power law function of y, which you have to find in your homework task. And the most dominant term is exponent of y squared. And please let's take a look. What does it imply for original function? And actually, it means the presence of this term means that psi has growth which is unbounded at large y, because psi becomes proportional to exponent of y squared over 2 at very large y. And now our task is to check how do we achieve of vanishing of our wave function at the boundary of the box. And this is our final step in this exercise. Most importantly, we need to recall that our wave function now actually lives in a finite space. It means that with all our change of the conditions in mind, change of the variables in the problem in mind, we only remember that psi of L over 2 in original variables should be equal to 0. It means from the other side that phi over L over 2 square root of h bar over m omega should also equal to 0. And here there is a simple but important point, is that note that actually we are looking for the ground state wave function, and it actually should vanish at both plus L over 2 and minus L over 2. And this can be achieved by simple symmetrization of our contour integral solution. Again, having in mind the cancellation of the leading exponentially growing terms, this is more than enough to construct our solution. And finally, our condition of vanishing wave function at the boundary of the box becomes, here we employ so-called logarithmic accuracy. So we substitute all powers of y by 1, as the leading contribution is of course governed by the exponential. So we come to the following equation. And this equation is, again, in the same logarithmic accuracy, chooses for us a proper value of n. And solving for it, we find that n is proportional to the exponent of minus L squared over 4 h bar times m omega. And of course, this solution can be improved, and in fact, it's possible to find not only the expression of the exponent, but also this prefactor. But this requires elaborate study of the asymptotics, in particular all these coefficients, and will be subject of one of your homework problems. So, but for now, let us summarize what we have achieved. We found out that if the box is large enough, then the energy of the ground state only slightly changes from its value, so to say unbounded value, which is h bar omega times, and this change is proportional to exponent of the following factor. That's it.